is actually called Virtual Local Area Networks, or VLANs. It's actually a very important topic in networking and something that you find in almost all networks. The slides I'm going to be using today are actually from the Cisco Networking Academy, and we have access to these slides from our education system. Okay, so before we start to discuss what is a virtual local area network, let us first actually discuss its motivation. Okay, so imagine that you have an office building. So let's say, for example, this is a floor in a university campus or something like that. Here, let's say you have offices, okay, and in every office you want to have a computer. Okay, so in every office there is a desktop computer that is installed, and you want basically to have a network connecting all of these computers. So the normal way that you would do that is that on this floor you would have one room where you would implement a switch. Okay? And then you would run cables. Typically they are run across the ceiling. You would run cables from the switch to every desktop computer on the floor. Okay? This is typically what we have. Okay? If you have another floor, you would essentially do the same. So you'd have another switch here. And then if you want the switches to be connected, you will go to one port of the switch and run a cable across the floors to the other switch. And then somewhere on another floor, there can be another room where there is a router, and you would have one port from the switches, or maybe one of the switches connected to the router. So if this router is the one that has access to the internet, okay, so for, let's say, this device, if this is device A, if this one wishes to actually access the internet, it will send the packet to the switch on its floor. The switch on its floor will send it to another switch, and eventually it will find a path to the router that is connecting to the internet, which we would call in this case a default router. This would be the physical topology, which we simply have been drawing throughout the course as something like that: a router connected to a switch connected to another switch, and then this one is connected to clients, and then this one is connected to another group of clients. This is basically what we're showing in the figure on the left, but in a more realistic or a way that represents more the actual physical topology. This is what we have been discussing. We know that the switch is a layer 2 device. So if device A wishes to send a packet to device B, which is on a second floor, it will put actually the source and destination IP addresses of A and B, and will put the source MAC of A and the destination MAC of B. Because the forwarding in this case will be done only by switches, then the MAC is enough. Once you actually want to send the packet to the internet, you will enter the source IP address of the sender, the destination IP address of the final receiver. It could be a server on the internet, for example. The source MAC will be that of A, and the destination MAC will be the MAC of the port of the default router that is connecting the devices. On the figure on the right, it will be actually the MAC of the port on the router that is connected to this subnet. This here would be a subnet in the network. This is what we have been have been discussing throughout the course. Now, imagine that on the same floor, you have actually these two offices that host employees working, for example, in the HR department. Okay, next to them, you have two people working in the IT department. And here you have two people working in finance. Okay, each one of these employees is a member of a particular department in the organization. And we can assume that different departments in the organization will actually have different networking requirements. For example, members of the IT will want more access, will want more availability, will want more reliability. They will basically want to be able to access all the devices in the network. HR will want actually to have confidentiality in their access. They will want their records and their traffic to be secure and not be shared with anyone else in the network. People in finance might actually be the same. every group of members in a particular department will actually require their own networking demands, will have their own networking requirements. Now, the way that you see the network connected here will actually make it very difficult to satisfy these requirements, because at the end of the day, everyone is connected to the same switch. Everyone is a member of the same local area network. All of this is actually a local area network. We go beyond the barriers of a single local area network once we go outside a router. So everything that is connected to the same port of the router is actually a local area network. Okay, so how do we satisfy their needs? This was actually a challenge that presented itself to networking designers in the late 1980s and early 1990s. And one solution would be is that you'd actually have to restructure the entire physical topology. If you have something like that, you make these people who are members of HR, you connect them to a switch, and then you have another switch that is not connected to the first switch. And for example, these are the finance people, you give them another switch. Basically, you have to have an independent physical topology for each department, which is incredibly expensive and very wasteful and is not needed as a matter of fact. The solution that they came up with is to actually be able to design something called a virtual LAN. So if we say these are our switches, okay, and here we have clients connected to these switches, and the switches are connected to each other. This is our physical topology. Basically, what we want is that we want to say that devices A, B, and C are members of a single network, are members of a same domain. For example, the A, B, and C are all members of the HR department. And then you have devices D, E, and F are members of a different department, and they have different needs. Okay? Even though they are all connected to the same physical LAN, okay, the same physical topology, we want actually to be able to create a virtual topology on top of that that reflects our actual administrative needs, our actual company hierarchy. Basically, what we do is we create what is called a virtual LAN, a VLAN. Simply, we say that A, B, and C are members of VLAN 10. Let's say we give it a number. Every VLAN is given a number, and the number serves as its ID. So A, B, and C are members of VLAN 10. While D, E, and F are members of VLAN 20. This information is saved in the switches so that the switch now knows what every device is actually a member of. So if I want now to isolate the traffic of VLAN 10 from the traffic of VLAN 20, I will simply tell the switches, these devices are members of VLAN 10 and these devices are members of VLAN 20, and you're not supposed to forward traffic across VLANs. Once you actually define a VLAN, you will be able to isolate the traffic from one VLAN from another. Okay? So if you define VLANs the same way as we do it in this figure, then you will be able to isolate communications from members of VLAN 10 from the communications of members of VLAN 20. So device A, in this case, would not be able to forward packets to device F because device A is a member of VLAN 10 and device F is a member of VLAN 20. It's as if you have created sub-networks. You have created sub-VLANs in the same physical VLAN. Once you do that, it's as if VLAN is a subnet and VLAN 10 is a subnet and VLAN 20 is a subnet. And in order for one subnet to be able to send traffic to another subnet, you would only be able to do it through a router. Okay? Since in this figure we only have switches, we don't have routers, then in this case, you will be able to completely isolate the traffic of one VLAN over the other. This is the concept. This is what they thought of doing in the late 1980s and 90s. And then they had to find a way to implement this concept. So how can they actually do that? Already there were IT networks all over the world. Companies had already invested millions and millions into their infrastructure. And so how can you actually convince all these people to throw away their devices and implement new devices that actually support this virtual LAN structure? They found a compromise. Basically, they thought, in a network like this one, who needs to recognize the VLAN IDs? Okay? Who needs to recognize that this device is a member of this VLAN and this device is a member of a different VLAN? Do the end devices, basically A, B, C, D, E, and F, do they need to be aware of what VLAN they are on? Think of yourself as a regular user. Once you log on in any network, have you ever been made aware of the VLAN in which this device is in? You are never actually made aware of this fact. You simply use this device, and it is possible, actually it is likely, that the device itself is not aware that it is a member of one VLAN or the other. So who is actually aware? It is actually the networking devices, the switches themselves. If this is S1, this is S2, and this is S3, the switches are the ones that are aware of the membership of the devices. So this actually presented a solution to network designers. Rather than throwing the entire network away and implementing new ones, you would simply just have to throw the switches away and implement new switches. What would the new switches actually have that the old switches did not? The new switches would be able to understand what is a VLAN ID. That is actually the only thing. In a switch that is VLAN aware, and obviously all modern switches are VLAN aware, what you can do is that you can go to S1 and you can say this port or this interface is in VLAN 10. Okay, so all the traffic coming from device A will come over this interface, and S1 would know that this interface is actually a member of VLAN 10. You would have to manually configure it. Okay, you go to this other port and you say this port, let's say this is F01, this is F02, and this is F03. You would go to F02 and say this is a member of VLAN 10. You would go to F03 and you say this is a member of VLAN 20. I will show you these commands on Cisco Packet Tracer in a little bit. Okay. Now, once you configure it this way, the switch will actually be able to know that these devices are members of these VLANs. So far, the solution is actually easy, because if you have a port on a switch that is connected to a single device, then this device can be actually a member of a single VLAN. So F01, F02, and F03 on the switch S1 are all connected to end devices, A, B, and D. So you can just specify that these devices are members of this VLAN. These ports on the switch F01, F02, F03 are said to be in a state which is called the access state, meaning that they are connected to devices that are members of a single VLAN. The problem is actually in the connections between the switches, the link between S1 and S2, the link between S1 and S3, the link between S3 and S2 as well. These links are connecting one switch to the other. So you will see here, for example, that switch S1 has to be able to carry traffic from both VLAN 10 and VLAN 20, and has to be able to tell S2 that this traffic is actually coming from a device that is in VLAN 10 or a device that is in VLAN 20. Because as we said, the end devices, devices A, B, and D, can be VLAN unaware. They can be unaware of the existence of a VLAN in itself. So when A, B, and D send their traffic, they're just actually going to send their traffic in the usual way, the usual structure of the headers, the usual structure of the IP addresses and the MAC addresses. Everything for them is normal. It is actually up to the switch to say that this packet is coming from a device in VLAN 10, and this packet is coming from a device in VLAN 20. So how do the switches support that? Through a new protocol that is called IEEE 802.1q. It is called a tagging protocol. The switch will actually add a field to the data link layer header that is called a tag. So the data link layer header will have the MAC addresses, the source and destination MAC, and the switches now will add a new field that is called a tag. The tag is basically the VLAN ID. So if a switch receives a packet from device B, and the switch is already configured that port or interface F02 is in VLAN 10, then all the traffic coming from B, the switch will assume that it is in VLAN 10. So let's say device B wants to send a packet to device C. Okay, so the path would be from B to switch S1. Switch S1 will have to forward it to switch S2, and switch S2 will have to forward it to C. Switches S1 and S2 will have to figure out whether this communication is accepted or not, meaning that they will have to verify whether B and C are members of the same VLAN or not. Okay, so if I configure F02 to be a member of VLAN 10, F02 in S1 to be a member of VLAN 10, and I receive a packet from B on F02, then I will know that this packet is a member of VLAN 10. So when switch S1 comes to forward it to S2, it will keep the same MAC addresses that B has inserted, and it will add a tag in this packet that says this packet is in VLAN 10, and it will forward this packet to S2. Now S2 receives this packet, will look at the source and destination MAC addresses, and will now learn that in order actually to deliver this packet, I have to send it over this port. Let's call this F04. Okay. So F2 now needs to forward the packet over F04. It will look up its table and will see whether F04 has already been configured to be a member of VLAN 10 or not. If this is the case, then switch S2 will have no problem just forwarding the packet to device C, because device C is also a member of VLAN 10. Now, if device B wanted to send the packet to device E, it will insert the source and destination MAC addresses. Let's just assume for now, it's a wrong assumption, but let's just assume for now that device B already has it. S1 will receive the packet from B and will add the tag that says that this packet is on VLAN 10. This packet will go to S2, will check the MAC addresses, and will know that to forward the packet to E, I will have to use F05, but F05 is configured to be on VLAN 20. So there is a packet coming that has a tag VLAN 10, and I need to deliver it to a device that is on VLAN 20, and this is not acceptable, so the switch will actually drop the packet. Okay. This is actually a wrong illustration, this just last part, because you cannot actually forward traffic between VLANs. I will explain why in a little bit. But for now, you can only communicate between devices on the same VLAN. Okay, so we said that switch S1, once you configure ports F01, F02, and F03, you configure them as access ports. And these access ports are connected to a single VLAN. What happens to the port that is connected to another switch? This port is not connected to a device in a single VLAN. In fact, this port is the one that needs to do the tagging. This is the one that needs to actually differentiate VLANs. So this port will actually be defined to be in the trunk mode. The trunk mode is where you can actually have more than one VLAN. Okay. Now, so the link that is connecting S1 and S2 has to be configured in the trunk mode. And it has to be configured in the trunk mode on both switches. So if this is interface F06 and this is interface F07, okay, you have to go to switch S1 and configure F06 to be in trunk mode, and you have to go to switch S2 and configure F07 to be also in trunk mode. Once you configure a port to be in trunk mode, then you can allow more than one VLAN to travel over this port, and these packets will be tagged with the ID of the VLAN that the packet belongs to. Now, the question is, can you actually have an end device to be a member of more than one VLAN? The question is, the answer is, typically you don't need to do that, but it is allowed. However, if you do that, if you want A to be a member of more than one VLAN, then you have to configure F01 to be also in trunk mode, so that this port will be able to differentiate the packets coming from different VLANs. Only a port in trunk mode can differentiate between packets coming from different VLANs. This is basically the concept. Once you create that, you will be able to isolate the traffic from different VLANs. You'll be able to isolate A, B, and C from C, E, and F. Sorry, from D, E, and F, because they are in two different VLANs. It is as if you have created two internal subnets over the same local area network. And in fact, what would happen is that when you assign IP addresses to A, B, and C, you will give them a different network address than the devices in D, E, and F. It is as if they are in two different subnets. So typically, you would associate a single VLAN with a network address, and all the devices within this VLAN will have actually the same network address. And if you have a different VLAN, even though they are connected to the same physical LAN, you will give them a different network address in this case. Okay. This basically sums up the discussion that we just had. This would be here, the figure on the right shows the physical topology. Every floor has a group of devices, and at the end, you have a room where you have a switch, and then you have different floors. Each floor has a switch, and each floor is connected to a group of devices. And then all the switches are connected to another switch that is connected to a default router. Here, you are actually assigning these devices to be a member of VLAN 2, and you're giving them this network address. This is, for example, the IT department. These devices are members of VLAN 3, and they are given this network address, and it is the HR department. And these devices are members of VLAN 4, and they are given this network address, and this is the sales department. This is just an example. Every one of these VLANs is its own broadcast domain. It's as if it is its own subnet. We know that in a subnet, you cannot actually send the broadcast packet to another subnet. You can only broadcast within the same subnet. If you send an ARP packet, it's a broadcast packet. It only reaches the borders of the subnet. You cannot actually discover the MAC address in a different subnet. You cannot broadcast in a different subnet. Once you create VLANs, you are creating internal subnets, and you are creating their own broadcast domains. So members of VLAN 2 will not be able to discover the MAC addresses of members of VLAN 3 or VLAN 4. They will not be able to broadcast the packet in VLAN 3 or VLAN 4. Now it is as if each one of these VLANs is its own separate subnet, its own isolated subnet. There are actually many benefits of creating VLANs. It improves security because you actually isolate networks from each other. Because you are reducing the broadcast reach, so you do not broadcast in the entire network, you are actually ending up with lower overhead, so you end up with better performance. The system is more efficient because the bandwidth is used in a better way, and it is easier to manage because now you can actually provide specific needs to each VLAN according to its functionality or according to its description. Okay. In every switch, by default, there are actually several types of VLAN. So if a switch has all these interfaces, if you go to Cisco Packet Tracer, you go to a switch and you say show VLAN brief, you will actually get all the interfaces in the switch and what they are a member of. By default, all the ports in the switch are members of what is called the default VLAN, meaning that there is basically no VLAN in the switch. By default, this is actually VLAN 1. VLAN 1 in a switch cannot be deleted. So by default, all the interfaces in the switch, so if this is a switch, by default, all the interfaces are members of VLAN 1, which is the default VLAN. You have to go to the switch and physically assign one of these ports to be in a particular VLAN. So in our previous example, when we said this port is a member of VLAN 10, you have to actually go to the switch, and I will show you the command in a little bit, and say this port is a member of VLAN 10. Once you do that, this is actually what is called a data VLAN. Once you assign a port to a VLAN, this port is actually called, this VLAN is actually called a data VLAN. Okay, these are the ones that are commonly used. There is also something called a native VLAN. Native VLAN is for the traffic that is generated in the switch itself. So the switch itself runs different types of protocols. For example, there is something called the spanning tree protocol, which is when you have several switches connected to each other. They have to communicate with each other such that their forwarding tree doesn't have loops, so that you don't actually have a packet ending in a loop between the three switches forever. Regardless of what STP does, STP is a protocol that runs between switches, meaning if this is an N device right here, if this is device A, this doesn't actually run the STP protocol. So the traffic in the STP protocol is generated in the switch itself and sent from one switch to the other. Because it is sent from one switch to the other, it has to be sent over a specific link that normally connects the switches to each other. But the traffic that is generated in the switch itself is not traffic that is part of any VLAN. Okay? So the traffic that is generated by the switch itself for a protocol such as STP, there are other protocols, by the way, there is the VTP protocol, this traffic is not tagged. The traffic is not actually a member of a particular VLAN, and so it should not have a VLAN tag. Only the data VLAN traffic should actually have a tag. So when device A sends a packet from switch S1 to switch S2 and then to an end client, there would be a tag that is added here and removed by switch S2, so that the final packet that is delivered to device B will not be tagged. But only the data traffic is tagged. Okay? The native protocols that are running in the switches, they generate traffic and they are sent over the links, and they are not they should not be a part, or they should not have a tag that is part of any data VLAN. So we assign a specific VLAN ID to this particular type of traffic, and it is called the native VLAN. Okay. By default, the native VLAN is the same as the default VLAN. So by default, the native VLAN is also VLAN 1. You can change it to something else, and it is actually recommended to be changed to a different number. Okay. And once you change it, the traffic that is generated in S1 that is a native traffic will carry the tag of the native VLAN. Okay. So now you have identified the traffic to be a part of the native VLAN. You have now differentiated, for example, traffic that is generated by the STP protocol from the regular traffic that is sent. Now, if you define, let's say this is F01, interface 01 on switch S1. If you define the native VLAN here as, for example, VLAN 99, you have to define the native VLAN on switches S2 and S3 to be the same number. So once you define a native VLAN to be a certain number on a switch, you have to go to all the connected switches and define the native VLAN to be the exact same number. So if you choose VLAN 99 to be the native VLAN on switch S1, you have to go to switches S2 and S3 and configure the native VLAN to be VLAN 99 as well. The final type of VLAN is called the management VLAN. It's a special type of VLAN that is used to carry network management traffic. There are many network management protocols. There is syslog, there is the routing protocol, there is SSH. There are many different types of network management traffic. And by default, the management VLAN is also the default VLAN, which is VLAN 1, but you can actually configure it to be a different one. In this case, the traffic from the network management protocols will actually carry that VLAN ID. Okay, these are the types of VLANs that we have. We talked about this figure. Basically, when you have a network like that and you configure PC1 and PC4 to be in VLAN 10, while PC2 and PC5 are in VLAN 20, these are two broadcast domains. And you will see here that the IP addresses of PC1 and PC4 are in the same network. They are 172.17.10.24/24. So the first 24 bits are 172.17.10. This is the same network address. For PC2 and PC5, the IP addresses, the network address is 172.17.20. So it's a different network address. So even though all of these devices are in the same physical VLAN, because you have defined now two different VLANs, you are giving them two network addresses, and so they are two broadcast domains. For example, if PC1 sends a packet with the destination MAC address all ones, it will be forwarded to S2, and S2 will tag it as VLAN 10. And it will be forwarded to S1, which will see the tag as VLAN 10 and will forward it to S3. S3 will see the tag as VLAN 10, will remove the tag and will forward it only to PC4. So even though this is a broadcast packet, the switches don't send it to everyone. They only will send it to members of the same VLAN in this case. So PC1 can only broadcast a packet in this case to PC4. PC2 can only broadcast to PC5 because they are members of the same VLAN. Okay. We talked about trunks. The trunks are basically the links between the switches that can actually carry more than one VLAN, and they are the ones that add the ID, the VLAN tag, and they remove also the VLAN tag at the last hop. So once S3, for example, needs to send the packet over this link to PC6, it will remove the tag and send the packet untagged to PC6. So let's say you have, for example, PC3 here sending a packet to PC6. PC3 will send the packet to S2 that is untagged, just a normal packet with normal data link layer headers, and all the other headers are the same. And this will include the source MAC of PC3 and destination MAC of PC6. By the way, PC3 can actually discover the MAC of PC6 because it can do ARP, can send a broadcast ARP, which will be forwarded from S2 to S1 to S3, and then to PC6, and the reply will come back. This ARP broadcast will not reach anyone in the network except PC6, because PC6 is the only one in the same VLAN. Okay, so we return. Let's say PC3 generates a packet, normal packet, untagged, sends it to S2. S2 will recognize that F06 is a member of VLAN 30. It would have to be pre-configured, and then it will forward the packet by adding a tag that carries the ID 30 to S1. S1 will read the tag and will forward the packet over F03, and the packet will reach S3, and it will now know that it needs to forward the packet to PC6. It will remove the tag and then forward the packet untagged to PC6. This is the requirement such that all the end devices can be VLAN unaware. They don't have to actually be aware about the existence of VLANs in the first place. Okay. This is then the structure of the tag that is added. Here you have the normal data link layer header. It includes source and destination MAC, the type of the packet, and the actual data. And there are some error correcting information in the end. The 802.1q is the standard that is implemented in the switches. Actually, it's implemented on all devices now, but typically the switches are the ones that use them, and they add this tag. The tag contains some information, especially what is called the VLAN ID, which is the one that identifies the VLANs. Okay, we discussed that. Cisco devices have a special VLAN for voice. As we know, voice is a type of traffic that is real time, so it needs special support. Okay, you need the switches to be able to prioritize packets that are carrying voice, so that they are delivered with a certain bound on the delay. Okay, so Cisco devices have a special VLAN. It's typically when you define it, you have to say this is a voice VLAN, so that the switches will actually provide it with special support. Okay. In our offices, we have something called an IP phone. An IP phone is basically just another device. It's just another end device in the network. But actually, the IP phone, inside it, you have a switch. You have a small switch that only has 3 ports. And you basically will tag the ports of the switches. One of these ports will be connected to the phone circuitry. And this port will be in the voice VLAN. And so it will be provided with special attention. And then there can be another port that is actually connected to the computer, and this will be a member of a different VLAN that carries actually the data that is sent to the computer in this case. Okay. So now let's see how can you actually implement a VLAN over Cisco Packet Tracer. The first thing you have to do is that you have to create the VLAN itself. So you go to your switch. Let's say this is switch S1. I know that you may have got this information from a few previous experiments. That's why I'm actually going to go over it quickly. So you go to the switch, you enter the configuration mode, and you just say VLAN, and you give it the VLAN number. So if you say VLAN 20, the VLAN 20 is then created over the switch. You can give it a name, but this is optional. And then you say end, so you exit that mode. Now you have created the VLAN over the switch database. Okay, so the switch now recognizes that there is a VLAN that is called VLAN 20. You have not actually assigned members of this VLAN yet. You just created the VLAN. Next, you can actually start assigning members. And assigning the members depends on whether the interface that you will define is in access mode or in trunk mode. So let's say you are in switch S1 and you want to define this port to be a member of VLAN 20. Okay, so you go to the interface. First, you have to go to the configuration mode. You go to the interface and you define the interface to be in access mode. You say switch port mode access. So now this interface is in access mode. And as we know, a port that is in access mode can only be a member of a single VLAN. So you just go to the interface and you say switch port access VLAN 20. So now you have defined that F018 is in access mode and it is a member of VLAN 20. The figure on the right shows you how to actually define a port to be a member of a voice VLAN. So first of all, you go to VLAN 20, okay? And then after that, you actually can create another VLAN and you have to say that this is the voice VLAN, okay? No, actually here you're just giving it a name. This is just for your own access. If you go to interface F018, you define it to be in access mode. You define it to be a member of VLAN 20. And then you have to say that this is actually a voice VLAN. This is the command that tells the switch this is a voice VLAN so that it gives it a certain priority to let the delay be bound. If you want to change the membership of a certain port, you can say no switch port access VLAN, and it removes the membership of that port. If you want to delete a VLAN altogether, you say no VLAN, and then you give it the VLAN ID, and the VLAN will be deleted. And by the way, if you say no VLAN 20, then VLAN 20 will be deleted from the database. However, all the ports that were assigned as members of VLAN 20 will now be inactive. They will not be returned to the default VLAN automatically. You have to go and you have to return them to the default VLAN, or you return them to another VLAN. But by default, they will not actually be returned to VLAN 1. If you want to delete all the VLANs, there is also a command to do that. Obviously, these commands have to be used with care so that you don't end up removing your entire configuration file. Okay. If you want to verify, there are commands. If you say show VLAN and you give it a certain name, you can actually see this particular VLAN. In particular, you'll see, for example, this is VLAN 20, and these are the ports in the switch that are members of VLAN 20. If you say show interfaces VLAN 20, it will show you actually all the interfaces that are members of VLAN 20. If you want to define now a port to be in trunk mode, this is particularly the ports that are connecting switches to each other. So in this case, it will be port F01 that is connecting switch S1 to S2. First of all, you will go to configuration mode, you will go to a particular interface, and you will say switch port mode trunk. So in the previous example, it was switch port mode access to define the interface to be in access mode. Here you say switch port mode trunk. And by default, if you say switch port mode trunk, by default, the native VLAN will still be VLAN 1. You can change it using this command. So switch port mode trunk, native VLAN, and then you give it an ID. Here, you're actually now defining the native VLAN to be VLAN 99. So all the traffic that is generated in the switch for protocols such as the STP protocol will carry actually the tag 99, specifying that this is a native VLAN. But you would have to go also to S2 and do the same. You would have to go to S2 and say switch port trunk native VLAN 99, so that both switches will recognize that this is a native VLAN and this is its ID. If you don't do that, you will get an error. So now you have defined this interface to be in trunk mode. The next thing you will have to do is to define what are the allowed VLANs. Okay. If you don't specify that, all the VLANs will be allowed. Okay. So it is optional. You don't actually have to say it. If you don't specify which VLANs are allowed, everything will be allowed. If you specify it, then these are only the VLANs that will be allowed. Okay? So here you're saying switch port trunk allowed VLAN 10, 20, 30, and 99, meaning that this port will only carry the traffic of these VLANs. If the switch receives traffic, let's say there is another port here that is connected to VLAN 15, and it receives the switch receives traffic from this VLAN, it cannot actually forward it over this link because the switch specifies that these are the only VLANs that can actually be used. If you want to return a link to the default state, you say no switch port trunk allowed VLAN, no switch port trunk native VLAN. Everything is then returned to its own default state. If you want to verify, you can say show interfaces, and here you will see that the interface is actually in trunk mode. Okay. As we said, we assign typically a different IP address to devices in different VLANs. So if PC1 here is in VLAN 20, it is given an IP address that has a network address that is same to everyone in VLAN 10. Now, the problem is, what if you misconfigure the IP address? So in this example, this device here, PC1, is given an IP address 172.172.10.21, and here you have a server that has an IP address 172.17.10.30. Now you have configured FA02 on switch S1 to be in VLAN 10, and you have configured F011 on S2 to be also in VLAN 10. So technically, both devices, both PC1 and the server, are members of the same VLAN. However, PC1 in this case will not be able to forward traffic to the server and not receive anything from the server because the server's IP address has been misconfigured. So it is necessary not only to configure the ports and the switches as to be members of the correct VLAN, you have to also make sure that they are all given IP addresses with the same network address. Okay, we have to think about that. Why is it that PC1 in this case will not be able to send anything to the web server? Okay, what is the networking process that would not allow PC1 to send traffic to the web server? Let's think about this for a second. If PC1 wants to send something to the server, the first thing it would have to do is obtain its IP address, and it typically does that from DNS. No problems there. Let's say PC1 has obtained the destination IP address of the web server. Now, the next thing that PC1 will have to do is that PC1 will actually have to make a decision. If the IP address of the web server is in the same network as PC1, then the next step would be for PC1 is to discover the MAC address of the web server. However, if the web server is in a different network than PC1, then PC1 will actually have to send the packet to a default router. Once PC1 realizes that the destination is in a different network, it will realize that it cannot forward the packet to it directly. This is how actually the protocol stack is configured. So PC1 will realize that the web server has an IP address 172.17.10.30, which is in a different network from PC1. Remember that PC1 and the web server are not aware that they are even members of the same VLAN. And even if they are aware, it makes no difference. Since it is in a different network, PC1 will want to send the packet first to a default router. Because as we said, if you want to send the packet to a device in a different network, then you have to use the services of a default router. So PC1, rather than trying to discover the MAC address of the web server, it will now try to discover the MAC address of the default router. In this figure, it doesn't actually exist. But even if there is a default router, PC1 will actually be trying to discover the MAC of the default router and then sending the packet to the default router. And then it would be up to the default router to forward the packet to the web server. This is actually why this communication between PC1 and the web server would not work, because the web server has been configured with the wrong IP address in a different network. And so PC1 will not be able to send the packet directly to it. It will want to send the packet to the default router first. Okay. This brings us to actually a step of troubleshooting. So this example that we just mentioned is a very famous problem that you would have once you actually have a device that is unreachable. So you are sure that you actually configured the VLANs correctly, but you are trying to send to the server and the packet is not actually reaching the destination because you gave it the wrong IP address. This flowchart here shows you actually the steps that you should do to troubleshoot a VLAN. So once you discover that there is no connection among devices in the same VLAN, you check, is the port in at the correct VLAN, meaning that you have configured the ports correctly in the VLAN? If not, then you actually assign the port to the correct VLAN and check again. If you confirm that the ports are in the correct VLAN, for example, here in this example, PC1 and the server are actually both in VLAN 10. So the problem is not the VLAN ports. You check if the VLAN itself is present in the database, meaning that did you actually create VLAN 10 in the database? If yes, then you have to check the IP addresses. This will be the final thing. Okay. If the link is a trunk, then there is actually a different flow chart. So the link that we just discussed before is actually an access link. If it's a trunk, then there is a different set of steps. First of all, check that the native VLAN matches on both trunks. So if you're getting an error, you have a switch between, you have a link between switch S1 and S2. You have to check that the native VLAN is configured correctly between S1 and S2. If not, then you have to change the native VLAN such that it matches. If they are actually correct, then you have to check the trunk modes, meaning that you go to the two ports and you check that they have been configured in trunk mode, that they haven't been accidentally configured to access mode. If yes, then you have an operational trunk. If no, then you have to configure both of them to be in trunk mode. There is another step that you can actually see if both these steps do not actually solve the problem, which is to check the allowed VLANs. Check that both switches have actually the same list of allowed VLANs configured. I will show you just some examples of these problems. This example here is in the incorrect port mode. So in this example, PC4 cannot reach the web server. They are actually configured to be both on VLAN 10, but once you do show interfaces, you see that interface F03 on switch S3, which is this interface, is defined to be in access mode, not in trunk mode. So to solve that, you have to go and configure it to be in trunk mode, and then you can actually start carrying traffic to the switch. So because this port here in S3 was configured to be in access mode, and it is a port that connects S3 to S1, it will not actually be able to carry the traffic. Here, this is actually an incorrect VLAN list. So again, PC5 wants to reach the student email server. They are both actually on VLAN 20, so this traffic should be allowed. And you will see here that they are both given the correct network address, so 172.17.20.10 versus here 172.17.20.25. So they are in the same network, so this is not the problem. But if you do show interfaces on switch S1, you will see that F03, which is a trunk, is only defined to be able to carry VLANs 10 and 99. However, the student email server and the student are on VLAN 20. So VLAN 20 is not actually allowed. So to solve this problem, you go to the switch and you say allowed VLAN 10, 20, and 99. And if you show interfaces again, you will see that FA03 is now able to carry VLAN 20, and this would solve the problem. Last topic I will discuss is basically how to allow communication across VLANs. So if VLAN 10 wants to send traffic to VLAN 20, we know that it cannot be done directly. So you cannot actually have a switch sending traffic across VLANs. Basically, the solution is to treat the VLANs as if you are treating a subnet. Once you have a device in a certain subnet wishing to send a packet to a device in a different subnet, the solution is basically they have to use a router. And there has been several solutions over the years. Typically, you have actually three solutions. One is called legacy inter-VLAN routing. One is called router on a stick, which is the one that is commonly used. And one is called layer 3 switching. Layer 3 switching is that you would actually buy a switch that has layer 3 configured. You have some switches that are a little bit more advanced. So they are still a switch. They still use MAC addresses for forwarding, but they can understand IP addresses. So they still use MAC addresses for forwarding. They still learn MAC addresses in the same way as a switch, but they can understand the subnet. They can understand the IP address, and so they would be able to forward packets across VLANs. We will not discuss layer 3 switches in this course, but we will discuss these two solutions, legacy inter-VLAN routing and routing on a stick. Legacy inter-VLAN routing is the old solution. It's no longer really used. The solution is quite simple. Basically, you want to have, let's say, if you go to switch S1, if you go to switch S2, you see F011 here. This is on VLAN 10. F018 is on VLAN 20, and F023 is on VLAN 30. And these two ports are trunks. Okay, so this is 10, 20, and 30. if you want PC1 to send the packet to PC3, they are on two different VLANs. So if the packet arrives at S2, S2 will actually drop it. So you will not actually be able to have S2 send the packet from PC1 to PC3. Legacy inter-VLAN routing solves the problem simply by having the packet go to the router first. So if PC1 wants to send the packet to PC3, it will actually have to send it to R1 first. The destination IP address will be that of PC3, and so PC1 will recognize that PC3 is a different network, and because it's in a different network, the packet will have the source IP address of PC1, destination IP address of PC3, source MAC address of PC1, and destination MAC address that of the default router. What you simply do is you go to S1 and you connect two interfaces to the same router. You define one interface to be a member of VLAN 10 and one interface to be a member, for example, of VLAN 30. Okay? And then when traffic comes on VLAN 10, you send it over the link that is configured as VLAN 10. Okay? The router will receive this packet, and the router in this case is treated as just another end device, meaning that the router doesn't have to understand VLANs at all. The router receives the packet with the source IP address and the destination IP address and will know that to deliver this packet, it will have to use this interface. Now, the packet is then forwarded by the router. It is carrying the destination IP address of PC3, forwarded by the router to S1, which will receive the packet over the second interface, which has been configured over the switch as a member of VLAN 30. So the switch S1 will now return the packet tagged with VLAN 30. When S2 sent a packet to S1, so when PC1 sent a packet to S2, it is untagged. S2 receives the packet, and the packet came from a port or an interface that is configured to be in VLAN 10. So when it sent it to S1, it carried a tag VLAN 10. Okay? And now it gave it to the router. After removing the tag, the router receives the packet, looks up its routing table, and finds that it needs to forward it over this interface to S1, and so S1 now receives the same packet untagged over a different port that is labeled to be a member of VLAN 30. So now S1 will forward the packet to S2 after adding the tag 30. Okay, S2 receives this packet. Now it receives the packet that is tagged with VLAN 30. It will remove the tag and forward it to PC. Okay. So now you've used the router such that it does routing between VLANs, and you avoid actually having to have routers understand what a VLAN is. Okay. However, the problem with this solution is that it uses too many interfaces of the router. The router is a very precious commodity, and you don't want to consume its interfaces. You're actually consuming two interfaces. You have to consume a single interface for every VLAN. Here, for example, we only have two interfaces, one for VLAN 10 and one for VLAN 30. If you want to enable routing from VLAN 20 as well, then you need actually a third interface between S1 and R1. You'd have to have as many interfaces as you have VLANs. And in many networks, you actually have so many VLANs that you would be consuming all the interfaces of the routers, which is a bad idea. Router on a stick solves this problem. Rather than actually having two interfaces connected to the router, one for each VLAN, you have one interface connecting S1 to the router, but you define this interface to be in trunk mode. Now you actually have R1, it has to be aware of the VLANs. You have to define the interface at the router to be actually in trunk mode so that it understands the tags. And now S1 can simply send all the frames tagged to the router, and the router will be able to understand which VLAN this packet is a member of. There is also an additional feature that in the routers that we will use, which is called sub-interfaces. Okay. Even though we're using only a single physical interface in the router, you can actually go and you can create virtual interfaces that we call sub-interfaces, meaning that it's as if you have a single port and inside it you have three sub-interfaces. These are virtual interfaces, so they don't really exist physically, but you can actually create them and you can give each of them a different VLAN ID. Let's actually see the implementation in Cisco Packet Tracer for both legacy inter-VLAN routing and for router on a stick. For legacy inter-VLAN routing, it's very easy. You go to the switch S1, you first create VLAN 10 and you create VLAN 30, and then you go to the interfaces, you specify F011 to be in VLAN 10, and F04 to be also in VLAN 10. You go to F06, you say that this is a member of VLAN 30, and F05 to be a member of VLAN 30. So you have to go to the switch and you configure all the ports to be members of different VLANs. So now PC1 is in VLAN 10, PC3 is in VLAN 30. You see here that they are given different network addresses. Okay, and now you want PC1 to be able to send to PC3. So now you have to go to the router. You go to the G00 interface. You just give it an IP address, and you have to give it now an IP address that has the same network address as VLAN 10. Okay, you don't have to tell the router that this is VLAN 10, but you have to give this interface an IP address that is in VLAN 10, so that this interface in the router is by default a member of this subnet. You don't actually have to make the router aware of that, but you have to do it based on the network address that you assigned to PC1. Same thing for the second interface of the router, which is G01. You have to give it an IP address in VLAN 30, so that the router now knows that this interface is a member of this subnet. It doesn't know that it is a member of the VLAN, but it knows that it is a member of this subnet. And now the router will treat a packet that is coming from PC1 and going to PC3 as if PC1 and PC3 are just members of two different subnets, and the router has no problem forwarding actually the packet between them. So configuring legacy inter-VLAN routing is easy. If you want to configure routing on a stick, first of all, you have to go to the switch. You create VLAN 10 and VLAN 30. You go to interface F05, and you configure it to be in trunk mode. In the figure on the left, it is still shown as two interfaces, but this is actually wrong. You only need one interface. You configure it to be in trunk mode, and that's it. You see here, we didn't actually specify which VLANs are allowed. It means by default that all VLANs are allowed. Then you have to go to the router and you have to go a little bit more configuration there. We said that in routing on a stick, the interface in the router has to be configured in trunk mode. So the first thing that you do is that you create your virtual interfaces. You go to, instead of saying G001 or G0/0, you go and say G0/0.10. Point 10 is actually the virtual interface. This is the sub interface. So now you have created a sub interface, and you will see here the prompt directly changes to sub IF, meaning sub interface. You have to specify that this is in trunk mode by saying that this is the encapsulation protocol that is used. This is basically IEEE 802.1q. This is the protocol that adds the tags. You're just saying that this is the protocol that is enabled on this sub interface. Again, you give it an IP address that is a member of VLAN 10. Okay, and then you create another sub interface. You say that it is also in trunk mode, and you give it an IP address that is a member of VLAN 30, and then you have to activate the interface by saying no shutdown. Okay, what you have done here is that you have created sub interfaces and you have created them in trunk mode so that they receive packets coming from S1 tagged. Okay, S1 will send now packets to R1 tagged, and R1 will be able to understand the tag because it will have these the .1q protocol enabled on the router. So now you can actually again send packets between PC1 and PC3. Final thing is just some verification commands. If you do show VLAN or show IP route, you will be able to see the sub interfaces, and you will be able to see the VLANs connected to these sub interfaces. You'll be able to see the routes as well. Okay. If you ping from one device in one VLAN to a device in another VLAN, obviously this will work. That's it for our course. I hope you have found it beneficial. I hope you have found it also entertaining. My best wishes for success in all your final exams and all your quizzes, and hopefully we'll be seeing you again in another course once this crisis is lifted. Best of luck. I hope you stay safe, and I hope you and your families are doing well as always.